Hi, I'm Doug Black, Editor-in-Chief at Inside HPC. And today at SC21, we're talking with Neil Day. He is Senior HPC and AI Product Manager at Hewlett Packard Enterprise. Neil, welcome.
Hi, Doug. Thanks for having me. Thanks for taking the time to talk to me.
Okay, great to be with you. Let's start with kind of an overall question. How do you define supercomputing in terms of speeds and feeds, and what are some of the more exciting developments you see happening at the highest levels of HPC?
Yeah, from a supercomputer and basically define it as a big machine essentially which solves really hard compute-intensive problems which require massive amounts of data crunching. Now, as you know, HPE and Cray have the triple crown on Exascale, where we are doing the Frontier system, the El Capitan, and also partnering with Intel for the Aurora system. Now, some of the trends we are seeing in this space here is how do customers use our system? For example, I'm going to use Lumi as an example, a supercomputer that we are working on. One of the first projects on it would be an atmospheric research project where they're going to try to simulate how particles are actually formed. With the current computing power that they have access to, they can only simulate about 8 to 10 particles. But with this new supercomputer, they'll be able to go much further, much more number of particles and get more accurate. What these supercomputers are doing is they're increasing our understanding of the physical world by narrowing this gap that we have between what climate, for example, in this case, climate scientists can actually measure and what they can actually simulate. Because if we can simulate accurately as close to reality as possible, that helps us simulate different solutions that we would implement for the biggest problems in the world, right? That's one of the ways the supercomputers are being used. There's another interesting change that is happening that we see is the convergence of HPC, traditional HPC, and AI. And one of the interesting case studies on this was the Gordon Bell Prize that was awarded last year at Supercomputing, right here actually, is where the researchers did some groundbreaking chemistry simulations. But what they did was, instead of trying to use Schrodinger's equations, they used a ML model-based approach. And they were able to do millions of particles in nanoseconds in picoseconds of time, but traditionally they would only be able to do a few 100,000 particles in a few nanoseconds. So it's these kinds of problems which are seeing over 1,000 or 1,000,000x improvement in performance is going to be a very interesting trend in HPC, because if in the future, as we know, the world of simulations could be merged with the model-based approach, which gives this enormous giant leaps in performance. So these are some of the trends that we are seeing in how our customers are using these systems. And one of the ways we're actually seeing it is we have a lot of systems which are mixed, where they have CPUs, GPUs, and different kinds of technologies, because our customers are trying to solve the hardest problems using different approaches completely, which requires different hardware, software, different optimizations in the stack, really.
Yes, that combination of HPC and AI just is tremendously powerful. So now we know that, as you mentioned, Exascale, we know that the HPE Cray EX is at the core of the first 3 US Exascale systems, the first of which will be installed later this year at Oak Ridge. Now, how have you all achieved that? What is HPE's differentiator at the highest levels of supercomputing?
Yeah, so whenever I think of Exascale and these really fast systems, I'm always reminded of a quote I read from Seymour Cray himself. And as it said, the quote goes something like, it's not just about building a fast processor. The trick is to build a fast system. Because what's most important here is data. And I know we hear that a lot, but what's most important in these big machines is you have the right amount of data at the right place at the right time so that these processors can process it. Now, we essentially have 5 big pieces in our solution, which we think are very unique and which is enabling us to deliver this kind of performance. First, our infrastructure. Our infrastructure is scalable, that you can go from hundreds to thousands to hundreds and thousands of nodes. It can support mixed workloads, so you can have different kinds of CPUs, different kinds of GPUs, and other processors that the industry is exploring, all within the same infrastructure. And it has to be really efficient, because some of these exascale systems are 20, 30 megawatts in power. So you have to figure out a way to cool this. You have to figure out, we have to have intelligent power management in order to be able to bring these systems down and up and actually manage power, so we don't have anything stranded anywhere. So the infrastructure is uniquely positioned with its power management and also dense liquid cooling. Now, second is, as I said, we have to move data at the right speed, so it is at the right place at the right time. That's where our exascale era interconnect comes in, Slingshot. What Slingshot is amazing at doing is to manage tail latency. So in a marathon, what do you care about? Do you care about the average running speed of all the runners, or do you care about the speed of the last person? That's what we are very good at with Slingshot, tail latency. A Slingshot can take a packet from a source and break it up and decide the right route to get it to the destination in the fastest possible manner and put it all back together there. So we have very fine-grained adaptive routing, which really shines in these big machines where the networks are really, really congested. Now, the next piece that we have is our software portfolio, which essentially puts it all together as one vertical optimized stack. We have the Cray OS, where we have resiliency and performance features put in. We have the Cray programming environment, where customers can use our integrated programming environment to specifically compile their code for the hardware that they have. This helps us get every ounce of performance from the hardware. The next piece is the exascale level processors that we have, the CPUs and the GPUs and the FPGAs that we are going to be using. And because our infrastructure is so flexible, we are able to support all the different kinds in the same infrastructure, and also the most power hungry processors that we have coming now and in the next several years. The last piece is fast storage. We have our cluster store product, which essentially feeds into the data story again, where you need vast amounts of data to process really fast. So what cluster store does is it's sitting right on the Slingshot network. And so the compute blades have a fast, thick pipe to get all that data into the compute blades, into the system memory for fast processing. So the interconnect, Slingshot, the Slingshot interconnect, the scalable infrastructure, our software stack with our processor support for different kinds of, and the highest end of processors, and the fast storage is what essentially enables us to deliver these massive systems and the massive performance at very efficient power delivery, power consumption, and density. So those are essentially the key things that we have in our product.
So if you had to identify 1, 2, 3 of the key major, most difficult challenges in building supercomputers at this level of power and scale, what would they be?
As I said, one of the challenges I think I already covered, I won't talk too much about, is how to move vast amounts of data to get it at the right place at the right time. And that's where Slingshot really shines. The other problem that we are really having a lot of brain power in the company is involved in solving is power. And we always think about power going up, but it's actually more complicated than that. As we see in HPC, I've heard several folks say the first rule of HPC, what matters is memory bandwidth, and the next rule is what matters is memory bandwidth. So as these workloads are getting more and more memory intensive, what is happening is we are seeing trends where memory is getting closer to the processing unit. And we are having technologies like high bandwidth memory integrated into the package, which is leading to more and more thermal challenges. So it's not just the power going up, the case temperature at which we need to maintain these processors is going down. So if you think of a unit called thermal difficulty, and the numerator is power, and the denominator is the T case temperature at which these parts need to be kept at, you'll see the numerator is going up, the denominator is going down. So this number is going exponentially higher. So we are just having like a lot of challenges, and that's where our Cray EX really shines, is to support these really top bin CPUs and GPUs with demanding T-case needs. And that is, and we actually charted this over the last 50 years, right? The curve looks exponential there, right? But the Cray EX platform is one of the most unique platforms in the world where we can cool these processors at, and this is very important, at a density which is unparalleled in the industry today. And this density plays in right with our slingshot story, because we do the dragonfly topology where we have all-to-all connections. And the more dense you are, the more copper cables you use. And when you hear copper cables, think cheaper and more reliable than optical cables. So our density, which plays in, which we are able to do with the warm water cooling, plays in with our slingshot story and our dragonfly approach. So we are able to provide unparalleled TCO to our customers for the most demanding workloads. So these are some of the problems that we have. And this is how I think like Cray EX is uniquely positioned to meet these challenges in the industry.
Okay, so really, we've been focusing on highest end supercomputing. Does HPE Cray have ambitions to bring these technologies to the broader HPC and IT markets? And if so, how do you intend to do that?
Absolutely, absolutely. In fact, this was one of, I believe this was one of Antonio's charters when we bought Cray, is how to get these supercomputing technologies into the hands of more customers with HPE's resources and supply chain, sales, and just the resources of a bigger company. Now, we are actively working on, I'll phrase the problem this way. Even our sales folks early on, they were like, this Cray EX, but how can I sell it to my customer who only have a much smaller budget? They don't have 50 or 100 or $200 million to buy the Cray EX system. So what we're working on is several product concepts where we take the key innovations of the Cray EX, which goes from the liquid cooling piece, the slingshot and the dragonfly topology, the software stack of the Cray OS and the Cray PE in order to get the most performance out of your hardware. And we are thinking of different repackaging concepts where you essentially can get smaller bytes. So you can get the same blade technology that we are developing for these exascale systems, but at your right scale. So we are actively working on bringing the key pieces of the technology, the best things, and scaling them down so that anyone with a smaller budget can also buy these exact same technology and get the performance at the scale that they want for themselves.
Okay, that's a whole separate and really interesting conversation. I'd love to have it. Yeah, but great stuff. Thanks for that. Thanks for your insights, Neil. And I hope you have a great SC21.
Thank you. You too.